Welcome to part 2 of this incline problem. The only difference between this problem and part 1 is the force applied is no longer parallel with your incline, but it is acting against your incline. So what I'm going to do is I'm going to actually give you a chance to pause the video and perhaps try this question out on your own before going over the video yourself. This would be a good time to pause. The first thing I'm going to do is draw the free body diagram and show us how it's different compared to the other problem, which contains your force of gravity, a normal force, and again there is a force of friction. Now this is the tricky part. I'm going to put this vector over here like this, and I am going to break this vector down into its x and y components that are relative to this incline. Breaking this component down for FA, we have an x component of FA. This is up the incline. I'm going to call this FAX. There is also a downwards component, a y component of FA, kind of the one that's pushing down against the incline. If we take a look at similar triangles, we have 28 degrees down here. If we want to analyze the angles as part of this 180 degree angle we have over here, we start off with our FG. Our FG is on this side. We know that this from the previous video is 62 degrees. If you're not sure of how this was found out, you can look in the other part 1 of this video. This was 62 degrees. We know this one here is 28 degrees. And breaking down our FG, we found in our previous video that this was our FGY, and this one here being our FGX. Okay. This angle is a 90 degree angle, which means if this is 28, this must be 62 degrees. If this is 62, the complementary angle, here we have this 90 degree angle here again, that means this must be the complementary one, meaning this is 28 degrees. Similar to the previous problem, if you have no idea how to tackle this problem first, why don't you start by breaking down FG and FA into its x and y components. FGX and FGY were already done in the previous video, so I'm just going to load them up here, and if you're wondering how we got to these values, you can look in the previous video. And here it is. Talking about FA, breaking FA down into its components. We're not going to be able to calculate FAX and FAY since we don't know what FA is anyways, but I think it's still good to get the components calculated and started up. So for FAX, we have our hypotenuse, the angle we know. Since the side we have is the adjacent side, this is our cosine of 28. Equals to FAX over FA, which means FAX is equal to FA times cosine 28. By default, FAY must be the opposite, and that being sine. So we have here FAY is our sine, 28 equals FAY over FA, and our FAY here, this is equal to A sine 28. We are going to use that later on in our equations. So pretty much we have everything set up. We need to know the pushing force, which is FA. Let's start with, since FA is going to be in both the x and y direction, why not we write that out first? So I'm going to start off with the x direction. In the x direction, we know that the acceleration is 0.57 meters per second squared. F net is equal to our ma x subscript. In the forward direction, that's pushing our box upward with Fa, with acceleration, is Fax. Against that, we have force of friction and Fgx. Very similar to the previous problem, except the only difference is now we're dealing with a component of our pushing force. And if we want to break that down even more, we know that FAX is FA cos 28. FA cosine of 28. And force of friction we know is mu times Fn. So we can write this as subtracting mu times Fn, and we know Fgx. Fgx over here is Fg sine 28 minus Fg sine 28. All of that is equal to max. We now notice that in order to solve this, we need to know what Fn is. Because we don't know Fa, we do know this angle, we know mu, we know Fg sine 28, we know the mass, and we know the acceleration in the x direction. So let's turn to the y direction, because the y direction does have Fn, and if we are able to find Fn somehow, we can solve this problem. In our y direction, we have our box is not moving or not accelerating in that axis. So we have ay is equal to 0. Since ay is 0, that means the forces pointing in one direction upwards must equals the forces that are pointing against that. Remember where I showed us this? Forces up equals forces down. So all the forces up equals all the forces down. And that down, I mean down along the y-axis, not directly down. So for upward forces, we have Fn. For downward forces, we have Fgy. And here is the difference between this problem and the other problem. We have a component of our pushing force downwards as well, along the y-axis. So that forces down is Fgy and Fay, both of them together. Which means we can substitute this up here. We can substitute that in our previous equation. So let's do that. Let's substitute Fn into our x direction equation. We have, as a result, Fa cosine 28 minus mu. Fn is Fgy plus Fay minus Fg sine 28 equals mass times acceleration in the x direction. Now that's a bit of a problem, because if you want to solve for Fa is in two places. Let's first break this down a little bit more. I'm going to change color. I'm going to change this color to blue. Fa cosine 28 minus mu, and inside the brackets Fgy, we know from the previous drawing before, this is mg cosine 28 plus Fay. Fay from up here is Fa sine 28 minus Fg sine 28. This is mg sine 28 equals to max. And again, the masses are not going to cancel since we have Fa's here with no mass in these terms. I'm going to bring mu inside these brackets. I'm going to distribute mu. I know this is getting a little bit algebraic, but of course we can always do a little bit more extra practice in math, can't we? So it's mu times mg cosine of 28. Now here is where a lot of algebraic errors happen. When you're multiplying mu in, don't forget this is a minus sign, which means this must be negative and that must be negative as well. Okay, I'll put in the red just so you can see that. So this is a minus, then this is mu times Fa sine 28 minus mg sine 28 equals max. We now need to get the Fa's together. In order to solve this equation, remember, we need to move everything to the other side of the equation except keep the Fa. Okay, so let's clean up this mess a little bit. To make this more visual, I'm going to rejiggle the terms around. I'm going to put this term over here, and so this term is side by side with that term. And here we have it. We have the Fa side by side. Similar to how you distribute a mu inside your brackets, what we can do is we can do the opposite of distributing, is to factor one Fa out of each of these terms. To do that, we're going to put some brackets around these two terms. I'm going to put a bracket here, and to factor Fa out, I'm going to factor 1 out of each of those terms, which leaves me with FA in brackets. Now FA is gone from this term. This is now cosine 28 minus mu, and FA is gone, so we have sine of 28. Writing out the rest, we have minus mu mg cos 28 minus mg sine 28 equals max. So we need to clean up everything. Similar to peeling an onion, you peel the outside layers first that don't have your variable. So I'm going to move these to the other side. To move that, I'm going to need to add them to both sides of my equation. Here I have it. It's added to both sides. So I'm left with FA cosine 28 minus mu sine 28 equals to max plus mu mg cosine 28 plus mg sine 28. Whew, we're almost there. Solving for FA, this is FA times, in brackets, cosine 28 minus mu sine 28, which means we're going to need to divide both sides of our equation by cos 28 minus mu sine 28. This goes away, and now we have it. FA is equal to max. Let's put everything in now. We have mass is 10 kilograms times 0.57 as our acceleration, plus mu is 0.11, mass is 10, gravity 9.81 times cosine 28, plus mass is 10 times 9.81 and sine 28. All of this over cosine 28 minus mu sine 28. And let's put all of this in our calculator. Notice I'm saving my calculations to the very last step, which means it takes away the chance of me making calculation errors earlier. Oh, and mu here is 0.11. 73.7 newtons, which rounds up to 74 newtons in total. Here we have it. We have the pushing force of the incline needs to be 74 newtons. Notice that this force is a lot bigger than the one we found in part 1. Think about it. If you're pushing against the incline, some of the force is being wasted in the vertical direction or the y direction, not pushing your box up the incline. And also notice how having that extra component along the y-axis is going to increase your normal force. If that increases your normal force, in turn that will increase your friction force. If you're pushing against the incline, you will increase friction, which also increases the amount of applied force you need to push your box up the incline. It's kind of like the problem where you had your box on the floor and you're kind of pushing down on it, trying to move it forward. You're going to need a lot more force to push it in that direction because some of it's being wasted in the vertical direction and also increasing your friction along the process. It's kind of similar to that, but on an incline. Well, hopefully this video was helpful and giving you a little bit more algebraic practice. Sorry it might have taken a bit long. I will see you next time.